for 10th difference something.
So not Stirling's or Bessel's formula. Stirling was clear.
So,
There's
so
problem
TK,
regarding Bessel's.
that also you try to try with Bessel's formula. What is the concept of that? You have some concept, na? Based on that, that formula is being derived. Yes or no? What is the basis for that? No basis. That is true, na? So just think for that basis and then you try to expand that actually. So that is left to you actually. You think for that. So can you see the PowerPoint?
Yes, sir.
Yes, sir.
Yes.
Okay. So that previous part you have to look for that actually for how that derivation is being done, basis of that, and then try to correlate and expand the things. And I hope you will get it. So just try it at least first. So our this next topic is actually this linear algebraic equations. So we should think that because once you do and modeling and simulation or anything modeling, so this is first sort of the equation we always get. The previous one with the data. So from all experiment, all practical, whatever you do, first you get a data. Then once after getting data, you have to sometime you have to calculate your values at in between or somewhere far away, somewhere not in that given range, some given range also, out of range also. So that's what you did your interpolation first. So once you have all of them, you always go for some sort of fitting there. So best fit you always go for linear equations and all this. So sometimes in some models you always end up with linear algebraic equations actually. So we need to think that how to solve them first. Okay. So in this case, what you have, let's say you have some equations. You have n number of the these equations with n number of unknowns. So here you see unknowns are x1, x2, x3, and keep on going till xn. So these are your number of unknowns actually. And from here, if you have n number of unknowns, and obviously you need n number of the equations so that those can be solved actually. So you have these n number of the equations. Now we can represent them in matrix form actually. So this practically makes it easier actually. It's just a way of representation actually. So in that case, you can write in matrix format. These are coefficients of all unknowns one by one here. So this A11 is coefficient of x1, A12 is coefficient of x2, and A13 coefficient of x3, and this keep on going till xn. So we'll multiply this first row of matrix A with this column matrix X. So you will get your equation 1 actually. Same way you will get equation 2, the second row of matrix A multiplied by this column again, X column, you will get equation 2. So this previous equation can be recovered back from this matrix. Now what we did here, that how can we solve all these equations actually. So for previous cases you can understand these can be solved by you can say elimination of variables. So you have n number of the equations. So if you have in some equation you will end up of only one variable, so you will get that particular answer actually. So somehow by eliminating something, you are reducing the number of variables in each equations by subtractions or additions in order to get at least a equation where you need one variable. Another equation where you have two variables, another equation where you have three variables, and like that only, so that you can start proceeding your calculations. Or it might be possible that somehow you get all equations in such a way that every equation would have just one variable, means one unknown which is unknown. So let's say if you are converting somehow equation 1 in such a way, let's say this matrix A, if you somehow has converted this to upper triangular matrix, it means this equation have one variable, this the second last would have two variable, third would we have three variable, fourth would have four variable. So you are going back in that way. So if that way you are doing some back substitution, which is you have just followed in all calculations so far, because you have converted everything into one variable for, then you have two variables, then three, then you are doing back substitution, back substitution. So that particular method is called actually for your Gauss elimination, right? Correct or not? So this is your first method
Yes,
here.
sir.
So where I would actually I have a slide. That fine. So so that is your first method there, that you converted a system of equations in such a way that one equation will have one variable, another variable two, then three, then four, and keep on going. So that way you are converting it to a upper triangular format, and upper triangular, or you can say the lower triangular also, because both the way it would solve actually. So if you are converting into the upper triangle, that's called a Gauss elimination method actually. So so what you have here, somehow you are converting it to a upper triangular one. So let's say how can we do it actually. So let's say this is your example here. You have here, these are the equations you have, 5x plus 3y plus 2z equal to minus 2. Then you have x plus y equal to 2. So your z coefficient is 0 here. Then you have this 2x minus y plus z equal to 3. Then you have here. So finally you have converted this into a this actually your matrix format, augmented matrix. Then you have converted, you did your row operations, and finally you have ended up this one. So that is your upper triangular the matrix here. Now from here, from this you can get z. From the second one you will get y, back substitution you will get y. Then third one, from again back substitution, you will get your x. So this we have covered in the last class, right? Then you have the means another method is Gauss-Seidel method here. So what the Gauss-Seidel did, you have just converted everything into a only diagonal matrix. Rest of the thing are actually eliminated now. You have just eliminated term on the upper side of diagonal and lower side of the diagonal, and then you are minimizing your back substitution part. Fine. So that is the means the another method here. So somehow you have this matrix is not visible. So in this case, you did here from here you converted it to the upper triangular, means only the diagonal one here. Rest of the things are not there actually. So this we were talking something back substitution from here. So this is the case you have for the means upper triangular, means only the diagonal one here. So you did again row means operations, and finally you ended up this here, that each diagonal will have just one only. Fine. So this we did also in the last class. Then we have also talked about this this example also there. just to convert this set of the equation into again a diagonal matrix where you got 1, 2, minus pi by 2, and finally from here you will get your unknown variables. This is the thing here. So finally, in Gauss elimination here, you have just minimized somehow the net substitution at the cost of additional steps. So practically, steps would become twice of Gauss elimination here, just to minimize the back substitution. Steps are here also double. Then you did LU, that mean the decomposition also. You have divided this matrix into two parts. One is lower triangular matrix, one is upper triangular matrix. And here in this combinations also you ended up this one. So in this expression here you got LUX equal to B. So UX equal to Y is being considered. So once your Y is being calculated, you can calculate this actually from here easily, again by back substitution part here. So this is also the another way. So I want you to choose any one of the method. Practically first you solve one question from means all of them, and just you should have expertise at least in one. Now this is part we have covered in the last class. Now the another way is that is a iterative technique. The previous one we have solved so far was analytical techniques. Those will give you 100% exact answer. Only thing they will have slightly maybe a more step, or I don't know, so whatever you want to say that. But sometimes we want to have a iterative techniques, because sometimes we want to just start the problem as early as possible without very less, you can say, conceptual or analytical power actually. So in that case, category you have these four, you have the many more also. We will talk about these four only. So once you have a Jacobi method, then you have a Gauss-Seidel method, then you have successive over the relaxation method. You have one more, the Richardson method. So two of you, these you might have heard already, your Jacobi method and Gauss-Seidel. Yes or no?
Yes, sir.
Yes, sir.
Yes.
So these are one more, the successive over the relaxation and the Richardson one. So let's see one by one what you have. So in Jacobi method, what you do actually, you have a equation. This is the iterative technique. So in Jacobi method, you want to have that matrix first or equation just to convert into the diagonally dominant ones, equations first, and then for each variables actually just like this. So you have the previous one, you have here n number of the equations here, right? So in this you can rewrite these equation in that format. You can write equation 1 into this format, that you have just x1 only. So you have this one, you take all other term to the left hand side and divide by this coefficient of x1, you will get this equation number 1, x1. Same way you can write equation number 2 for x2, equation number 3 for x3, and equation number 4, and keep on going. So you are just writing each equation for each at least one variable. So first equation you wrote for variable 1, second equation you wrote for variable 2, third you variable 3 and 4. Why we have second diagonally dominant? So this should be chosen that which equation can be written for which variable. Just keep in mind only this coefficient here. So if you are talking about equation 1 here, you have coefficient a11, a12, a13 and a1n. So here keep in mind, just choose the highest element. The diagonally dominant one means here you choose the variable for which this coefficient is highest here. So let's say for this first equation that highest coefficient is, let's say, a11, highest. No matter whether it is minus or plus, it doesn't matter. You talk about the magnitude only. So in this case you have this a11 is the highest, so you wrote this equation for only for a variable 1. Suppose in case this is the highest one was a12, so you have to write this equation for variable 2, not for variable 1. So that's in the condition that's called the diagonally dominant one. So you are just considering the variable need to be calculated from that equation whose coefficient is highest among the and other coefficients. Is that fine? Hello?
Yes, sir.
Yes, sir.
So you have
Sir.
to convert in dot way. Don't convert them blindly. That equation one I will write for x1, equation 2 x2. No, don't do that one. So therefore, you just compare the coefficient of all unknowns and just take that unknown whose coefficient is highest only. Then you can write this one in this particular pattern. Now for that, as we were talking, these are the iterative techniques. Easy to understand and just have some computational time actually. So we will get the answer nearly to analytical one here. Not exactly same all the time actually. Close to that, not exactly same. So in that case, first, how would you proceed? So to proceed it, first you set actually your all unknowns equal to 0. That is first set. You just check it, everything is 0. Step 2, go back to this particular mean the equation. This is the general form, or if you don't understand this for time being, you can go back to this previous one. Convert this into in this particular format in diagonally dominant one, and then you substitute your x2, x3, x4 and all other variables into that. You will get a one new value of x1. Same way for the second variable, substitute all values which you have considered 0, 0 for all. Substitute there, so you practically you get here b2 by a22, b3 by a33 and b4 by a4, like that. This would be your first set of calculation. So now you got one set. So that is your one set. So you got a new set of x1, x2, x3, x4. Now go back again back. Now you know the values of x1, x2, x4. Substitute here back again all the values. That would be your next set of your variable x1. Now each step you calculate the difference. What is the difference? My calculated value at present x1 new. What was the x1 old? Calculate the difference. If this difference is not changing, you have to also fix your significant digit or tolerance. Let's say you want to have a consistent value, let's say 4 decimal places. So you check your, if the difference is going, let's say 1 into 10 to the power minus 5, it means you are making the consistency of 4 decimal places. So that's difference you are fixing the tolerance. What should be the difference or between two values of calculated one or old one? This need to be calculated at every step. When this fulfilled, it means you stop your iterative procedure here. So that will continue here. So you got here step 3, you got all variables, you just go to time. Step 1, calculate the difference, and the time the difference is in your given tolerance, you are the only person who will fix it up. Just like that, if you are doing money calculation, if this equation belongs to money, so if the difference is coming, let's say 1 rupee, if you are talking about the Indian currency, difference is just 1 rupee, because if you are just calculating difference 0.1, 0.001, it's meaningless, right? Because there no transaction in that money. So that how much you tolerate, that will come from your system property or what process are you calculating, that depend. Let's say you are calculating this or something, fugacity and all this. So you know the fugacity, the highest value is 1. So you have to give the difference tolerance at 10 to the power minus 3 or minus 4. Depending on that, you are fixing what should be my tolerance. It is not a general rule that 10 to the power minus 4 need to be considered, or a 0 need to be considered, or 1 need to be considered. Okay, so that is first thing, and keep on iterating the things till you get that particular tolerance. So that is, so if you want to write a general formula for the previous equations, you can generate all these equations from this formula, and this type of formula will help you in case of writing the program, because I want that you have to write program for each and every technique which we are talking here. So here, if you write in program case, you write a general form because you cannot write it for n number of times, addition, addition, addition. So somehow you have to think, how can I write in I and j form? So I can run a I loop, I can run a j loop, and so that I can use. So this would be your general expression for that. Is everything clear so far for this Jacobi method?
Yes, sir.
Yes, sir.
Okay. So next is Gauss-Seidel method. So Gauss-Seidel is slightly advanced than the Jacobi one. In Jacobi, you have taken all zero zeros, you have the substituted the zero everyone, you got new set at end, replace the old set and keep on continuing. Gauss-Seidel has slightly advanced. What it did, initially you have taken zero, okay, fine, because you don't have anything in the beginning. You have calculated based on your x1 variable 1. Now in equation 2, just put all unknowns which were not known previously plus one unknown you have just calculated back. So you have now calculated your x1. So at the place of x1 you just use your new value. Now when you move the equation number 3, so you know the value of x1 new also, you know the x2 new also. Substitute that back also in equation 3.1. So that way you are just converting it faster. So that we can see here. So what you have here, same equations we are taking and number of variables here. So we can write same thing we wrote in the previous one. Previous one also we have take about diagonally the mean the dominant one. Based on that we wrote equations for x1, x2, x3, x4. So first equation is same, no change here. Second equation, there's slight change here because here previous one you were also considering here old, everything was considering as old, but here is not. Here whatever you got here x1 new, now this new is coming to this one here. Rest of the things are old because these are not known to us. So I mean to say that in this method, whenever you have a new value of that, update that by uh, old one actually, replace the old one by the new value. So in case of third equation here, now you know the value of the x1 also new value, x2 also new value, but x4 you don't know because x4 is old. So same way for the time you will go for x4, you are having value of x1 new value, x2 new value, x3 new value, but you don't have x5. So if you x5 would be old here. So that way you are keep on updating by replacing old values by new values. So you are going in this way you are having convergence rate is faster as compared to the Jacobi method. So if you will write this thing in a general formula in terms of I and J, so you can write in that particular format here. The same as previous one, what you have in this side here, if you are calculating xi, means let's say you are calculating x2, it means you know the value of x1 already because that is being calculated. So that is coming here. These are the new values one. These are the summation of old values part. So you have two part here. One is will change from I less than 1. One is from I plus 1 until xn. So that way you can generalize this particular formula here. Procedure is same as previous. First you take 0, calculate x1, x2, x3 from the previous one. Now here previous and you can say the relation here is same. Now new set here would be generated again. So new set at last, the time you will calculate the last value, you will have all new set. Go back again step 1 and keep on updating the way and again the tolerance. Each step you are calculating again the tolerance. Once a iteration is complete, after that you calculate tolerance in x1, tolerance in x2, tolerance in x3, tolerance in x4, all variables. It's not just you are taking only one variable. No. Sometimes it might be possible for one variable you are within tolerance, but other variable you are not. So you have to tolerance for keep tolerance, check the tolerance for all variables. Once it is satisfied for all only then you will stop your iteration process. Is that fine?
Yes, sir.
Ah.
Yes, sir.
So this is your Gauss-Seidel one, and this you have here, and I wrote this 2 times. Yeah, I have not deleted this actually. The another method is successive over the relaxation method is same as your Gauss-Seidel one. So this is what you are getting from your Gauss-Seidel, but you are just taking the weight average. Means weight average means you are taking some component of new calculated value, some component of the previous value, and taking the means some sort of the weighted as means the average, and that's why you are having a weight function here W. So this way, this weight function is being fixed by you actually. It will not given by anyone else, neither by me or anyone else. It is you. You have the freedom to choose how much weightage you want to give it to that. But based on previous people practice, actually, they have given the range for that. That how much range will it go? So this is same thing. Only thing the new value is calculated by this way that you have given 1 minus W weight fractions to your previous value, W for a new updated value, and just calculated the procedure from your Gauss-Seidel one. But only thing to update a new value, you just calculate it from here. Is that fine for this explanation?
Yes, sir.
Okay. So only thing you
Yes,
have
sir.
just put a weight function there. Now this weight have some range here. So this is just to accelerate the conversion. If you are just putting this weight from 0 to 1, it is called under relaxation. If you are just putting value from 1 to 2, it is called over relaxation, means you are going wait, this is not change. So slight change here. Okay. So this is over relaxation. The time you will put your W equal to 1, you will go back to your Gauss-Seidel, because in this, if you change the W equal to 1, this term will completely cancel. So you will just get your Gauss-Seidel one. Okay. So these are the way. Also, in generally people take it nearly 0.5 for each of calculation there actually. So you can also choose that way, and you can also make your program and calculations. Another method is modify the resorption method here. So this also takes some weight function actually, but it follows your Jacobi method actually, not the Gauss-Seidel one. So you are calculating this from Jacobi method and just adding these a weight here W and just to these values. So you are the updating this only. Here you are not putting this the updated value. Means whatever value you are calculating in set 1, all of them you are multiplying by a particular weight, adding into the old one, and that would be your new set. Now new set would be used in a next trial only, not in between, just like a Gauss-Seidel one. Okay. Hello.
Yes, sir.
Yes, sir.
Yes, sir.
So these are 4 iterative techniques we have talked about, and based on that, you have to solve your questions actually. So this is the problem actually for this. Maybe just to test it, we can test it. This is purely from mathematics point of view. Then I can give you another problem. I think you focus on chemical engineering. Forget about this question. Let me give you a chemical engineering problem, because there you will find, I think, much more interest. Yes or no? So
Yes, sir.
give you. Just give me 2 minutes. Let me find it. Where that problem is. Yeah, this one. So what you have here, you have this question here. I think you will see that. Can you see this question? If water is flowing from the overhead tank at a level of 200 meter, water level in the tank is 10 meter all the time. Piping network is at 10-meter level from the ground. Various pipeline details are given to you. So these are the line one, this much length. This is the figure, it's something like that. So here, what you have here, you have an overhead tank here. From here, water is coming and getting distributed into the so many places actually, just like a hostel in your hostel distribution of the water supply something. So what you have here, you have an overhead tank, and then it is going to a different hostels and all this. You have a lines, and somehow at the end of the day means you are getting connected to here. This is just a problem to here. So what you are supposed to hear, you have the detail of each line. The length is given for each pipeline. For this pipeline, length is given L1. Line 2 also 2000 meter, line 3 3000 meter, line 4 4000, and all these length is given, diameter is given, roughness of each pipeline is also given. Okay, the roughness is given for each pipeline, that this is what the roughness is. Now pressure here is also given at 0.4, P4 is 2 atmosphere. Here this is overhead tank open to atmosphere, so at this particular place the pressure is atmosphere only. What you are supposed to calculate? calculate the discharge coming out from the overhead tank. First, you have to calculate what is the flow rate coming out from this particular tank. After that, find the pressure drop and flow rate in each pipeline. What should be the pressure drop in line 1 means delta P, in line 1, line 2, line 3, line 4, line 5, line 6, means how much the delta P. Okay, then find the pumping power in each pipeline. Means what should be the capacity of pump that need to be put in each pipeline. After that, calculate the power of a single pump. If you want to have a just one pump, rather putting so many pumps in each pipeline, if you are putting a single pump, which can be installed at point 2 is here. If you are just compensating all the losses by just putting a one pump, which you want to put at point 2, what should be the power? And as you know that single pump is much more better than the multiple pumps due to so many problems. What are the problems? First, multiple pump will need a multiple powers, man powers, difficulties, operational also, maintenance also. At the same time, you need here means changing in the flow rate means output wise also. So these are the constraints. So we always have a single pump in that we prefer. Now for that you have to formulate your equations first. Let's see what equations, so how much you know in fluid mechanics that will come out from this question itself. So this is the first question you have from your fluid mechanics, and as I taught you this simultaneous algebraic equations, so obviously whatever will come from here would be a algebraic equations actually. So can you proceed? What is to be done? You have this question. Can you hear me or nobody there?
Yes, sir, we can hear you.
Yes, yes. So now you start thinking and working what to do. You start doing on paper. You have to do it here only. I won't. I will leave the something to home, but not too much, because nobody is doing anything at home uh, due to so much pressures from other sides and this, that, and all this. So it's better to have your pen and pencil here. Turn on your video and just show me what are you doing. Yeah, turn on the video and let's see what are you doing, or how would you proceed actually. What will you do? Think for first question itself. You have an overhead tank and you have to find a flow rate. How would I calculate the flow rate? What should I do?